Josh Whitman, CEO of Whitman Technological. So the next step on our Nephele 2 robot project is to try to get an assembled axle with that very first gear. We're going to start to put the pieces of the axle together, and then we can measure the axle and figure out how big the gear needs to be, how wide it should be, so that it's the right spacing, so that it clears the edge of the tire properly for the gears to mesh with its teeth. All kinds of different stuff. We need to sort of put it all together in virtual space, and then we can start designing the gears. And once we have our first gear, we'll test all our measurements out by 3D printing that gear, and we'll actually assemble that axle and see what happens. In this video, I'm using FreeCAD for arranging all the pieces, but I'm using a new workbench called A2+. It's an assembly workbench, so it's meant for taking parts and sticking them together according to rules. So like the inner circle of the wheel has the same axis as the bolt does, so that makes the bolt and the wheel line up with each other, and in theory it's like putting the bolt through the wheel hole. So we use a bunch of rules like that in A2+. The video skips around a little bit because I'm learning how to do it. I've never used A2+ before, so I'm watching tutorials, reading the wiki, and practicing with stuff. And so I'm pausing the recording and then starting the recording again, and I didn't catch all of the progress, but I got most of it. I think you can see what happens. And I'm also using a new workbench called, well, new to me anyway. It's called TechDraw, and that is awesome. I love that so much, where I could take, essentially it's a 2D picture of the 3D objects as they're being assembled, and put them on a sheet of paper and then select specific points on there to measure distances between points or vertical and horizontal distances. So you'll see quite a bit of that, and that's also brand new to me. So I'm really excited to see it, though. I was able to just go and say, okay, well, once we put this together, if we have the nut and the bearing and the nut on the very outer edge of the bolt, then how much space do we have from the edge of the wheel to that nut? And then how much space do we have inside the wheel pocket in the rim for where our gears are going to mesh in with the spokes on the hub, so that our gear is actually not just squished against the tire to hold it so that it rotates along with the tire, but it actually has teeth that will notch into the spokes on the wheel so that the gear and the wheel really can't slip against each other at all. And we use a lot of measurement for that. And then I took the finished gear. The gear that we're using it's called a herringbone gear. 3D printing can do herringbone gears really easily, which is awesome because they're very difficult to machine. You typically, if you're going to machine it out of metal, you have to machine one angle of gear, and then you machine another angle of gear, and then you just bind the two together somehow. You bolt them together, and that's your herringbone gear. But 3D printing, you can just print, and it will just print both angles. It's not an issue at all for 3D printing. And the cool thing about herringbone gears, there's two things. First is when you just have a normal gear and its teeth are engaging, there's a slight kind of, as one tooth is slipping off and the next tooth is coming on, you end up having just this little bit of either backlash or extra noise that you're making because it's the engaging and disengaging is happening in a very kind of chunky sort of way. So if you put the teeth at an angle, then as they start to engage with each other, the front part is engaging while the back part is releasing, and you end up having the teeth more or less being constantly in contact with each other as the gears rotate. The problem is that if they're all going in the same direction, this starts to push the gears out of alignment. They create torque against each other because their teeth want to slide in the direction of force. So when you have some teeth going one way and some teeth going another way, then those two forces cancel out, and it eliminates that kind of sideways pressure that you get from the teeth. So a herringbone gear is a really cool kind of gear to use for continuous power transmission that kind of eschews all of the troubles you might have with other styles of gear. So hopefully those work out well for us. We'll find out. A lot of times I try something, it doesn't quite work the way I expect it to, so then I try again. I have like 200 or 300 printed parts of stuff I designed that didn't work the way I wanted it to, and I ended up having to print another one that was a little bit different so that would work to address whatever problem I had with the first one. And some things I've gone through 5 and 6 iterations of the design to figure out, like, oh, that doesn't work because of this. Oh, and now this doesn't work because of this. And slowly gets better and better until eventually it's a workable product. So we're going to watch the stuff get all laid out in FreeCAD and measured, and then building up that herringbone gear that will engage with the tire. And then I'll come back with you after we're ready to go. Okay, so we have our gear. We plugged it into Slicer. Slicer took it and cut it into little, there's like 5 per millimeter. It's about 0.2 of a millimeter is the thickness of each layer that the 3D printer is going to put down. So it's putting these 0.2 millimeter layers of plastic one on top of the other and slowly assembling the part vertically. So now we're going to take what we have from Slicer, which is G-code. It's a set of movements just like the laser did in the CNC laser video. Same thing, we've got G-code that specifies X and Y, and then there's an E coordinate, which is the extruder, and that says how much that needs to rotate to feed the right amount of plastic out the nozzle and onto the part as it's moving from one point to another. So it's passing large sequences of these codes to tell the printer exactly where to move and how much plastic to put out. So let's watch that part get built. It took 5 hours and 45 minutes for this part to print. It took an eternity, but we're going to see it all happen in about 20 seconds. All right, so now we have our part. The printing came out really nicely. So here it is, right here in my hands. We took something that we designed with our imagination and we 3D printed it into real life. And the goal was that if we assemble the entire axle, then we'll use the full 4-inch length of the bolt. So if we put this thing together, that last nut should tighten down against the outermost bearing and be flush with the tip of the bolt. So let's see how our measurements came out. First, we've got our bolt axis, and then we put the outer bearing on here, and then we've got the wheel. And you'll notice the side that's going to go against our gear has the 3 spokes, and we have 3 notches in the top of the gear, and this actually came out beautifully where that is just perfect. There's no wiggle room. It slots right in and it's nice and tight. So now we put the gear on, or the wheel on, and then we put the gear on there, slot it into the wheel. Then we put a nut over the outside to hold this whole mess together. Slowly but surely, we're getting there. Tighten it up as well as I can. Okay, now we've got our outer bearing there. And finally, the nut. And let's see how close we get to being perfectly flush. Boy, that's really good, huh? That's pretty nice. So there it is. The first part of Nephele's foot coming together. We've got our herringbone gear, we've got our axle, and now we're going to have to design the parts that will mount against the bearings and come up, and then we'll have our motor housing, a couple more gears to connect the power from the motor into the axle, and then something to mount on there, and then we've got a few more steps after that we'll be doing in subsequent videos. So far so good. I hope you enjoyed today's video. Hit that like button. Please subscribe to the channel. When we hit 100 subscribers, I'll show you my top secret laboratory. I'm Josh Whitman with Whitman Technological. I love science, and I hope you do too. Thanks for watching.